ARMA, RIMA, GARCH, eGARCH, whatever you can imagine, VAR models, VEC models, everything that the process is the same. And the process is called the Box-Jenkins procedure. Okay, so and the Box-Jenkins procedure, guys, works in the following way. So first of all, guys, remember, we call this step 0. Okay, the first step is to determine the stationarity of the data. And this is crucial because at this point, what we're doing is we're working with models that are prepared for stationary data. Okay, so stationary data, guys, basically means that we have data that looks like this. Okay, we don't have data that looks like this, for example. Okay, so these are basically representation of prices. Prices are not stationary, and these are representation of returns. Okay, so in finance, we're okay with this. So we don't have issues. Okay, so the first thing is to check. How do I check stationarity? What we are going to be doing, guys, is there is a formal test, but we're not going to do the formal test here. But at least we're going to see the autocorrelation functions, the ACFs. Okay, do you remember how was the ACF of the unit root test, of the unit root? Remember, we said that exists a unit root. For example, if I have a model like this, okay, so let's call mu plus, okay, so psi1 yt minus 1 plus my error. And we say that the unit root happens when this one here equals to 1. Okay? And what is the ACF of a unit root? Basically, the ACF of a unit root, guys, is going to look like that goes to 1 and then basically stays there forever. This is going to be okay. And my PACF is going to look like that and then disappears. Okay, so this looks like an R1 process, do you agree? Of course, very, very not decreasing to the mean. That's the point here with non-stationarity. Okay, so we're going to do that, and we'll show you how to do that. Once we have a stationarity proved, guys, we're going to move now to the Box-Jenkins procedure. That is basically, we need to select the model. How do we select the model? Okay, so when I say select the model in this first part, I'm talking about, do we have an R? Do we have an MA, or do we have perhaps an ARMA? Okay, so determining the model is basically determining also the lags, you know, and I will show you how to do that. Well, for here, we're going to use the visuals. Unfortunately, the visuals, guys, don't work in real life, but you know the visuals for an ARP process. How do you see an ARP process, guys, and how do you distinguish with an MAQ process? So, for example, let me delete this part here. So for example, guys, if I present you this graph, this is my ACF, this is my PACF. Okay, so imagine that I have and this continues eternity. So what do you think is this one here? So in another circumstance, I have something like that. What do you think, more or less, what do you think, which model do we have here?
First one is the MA3, I think.
Yeah, the first one, yes. Remember that the MA process, the ACF of the MA process disappears up to a given point in the ACF. And indeed, what you count is you count 1, 2, 3, disappears, and the PACF of a MA process goes like that, decreases asymptotically. So indeed, this should be, you know, an MA3. And what about this one here?
AR1.
Exactly. This looks like an AR1. Okay, so in theory, guys, and in the graphs that I'm doing here, you should be able to find that. But in real life, it's very tricky to find that. Okay, so we're not going to rely on visuals. We're going to rely basically on information criteria. Okay. So an information criteria, guys, what we're always going to try to do is we're going to try to minimize the information criteria. Okay, so the goal is to minimize the information criteria. Here we're going to basically deal with a bunch of them. So we're going to have the Kaike information criteria. We're going to have the variation information criteria. That is also called the Schwartz. And then we're going to have another one that is called the Hanan-Quinn. Okay, so basically what they try to do is they try to find a balance between including more lags and the balance of more volatility, right? So this one here is simply looks like that. This one here is very similar. And this one here is basically kind of a mixture. Okay. What is interesting, guys, is that this one here, the variation of the Schwartz, this one here is consistent, but unfortunately is not efficient. And the Kaike, guys, is not consistent, but it is efficient. Okay, I will show you how to use this stuff also here, guys. Now, there is a general rule in time series, guys, that is called parsimony. So what is this parsimony idea? That indeed what we try to do, if we have two competing models that they are very close to each other in terms of the information criteria, for example. So what we try to do is the one that has less number of lags. Okay, so we want a model that is more flexible, smaller, and can help us better explain or forecast the data. Okay, so this is a concept that you're going to have always in your mind, guys. And this is something we're going to be working with. Okay, once I have the selection of the model, guys, we simply go and estimate the parameters. So basically, we run again, we select the best model, and then we simply run again, and then we know the parameter values. Then what we do is we do a diagnosis and testing. And what is the main assumption here, guys, to remember about the UT? What is the main assumption of UT, of this error? The main assumption is that this one here is a zero mean white noise process. Do you agree? So, and the white noise process, guys, implies basically that the error of UT there is going to be zero. My variance of UT is going to be a constant. And my covariance of UT with UT minus J, any J, is always going to be zero for all J different from zero. Got it? So there is no a correlation, there's no covariance between the errors. So one way of testing, guys, that if we indeed have a good errors, is simply test and check if errors are basically white noise process. Okay, now remember, guys, that the white noise process is simply a stationary process. Do you agree? So that's what we discussed the last two previous classes. The stationarity is a general concept. Then we have a weakly stationarity. Then we have white noise process. And white noise process is by definition a stationary process. So what we can do is simply we can check the stationarity of the data, right? And then basically what we're doing is we're going to be verifying that the errors are not correlated. And finally, guys, what we're going to be doing is once we have this one here, we're going to start forecasting. Okay, so this is the process. And we're going to do this process very quickly. Okay, so now I think we can go into reviews. share. Let me open this one. Let's go here. Okay, so here we go. So this is my e-views, guys, and the date, I already prepared everything for you so we can run this quickly. But the idea is that you are going to receive only this data, okay? So this is Alcoa. You have daily observations, 2,810 daily observations. We can take a look to the, are you with me with the e-views file?
Where did you pull the data set from, Professor?
Yahoo Finance. These ones here are Yahoo Finance, all of them. But the file, you have the file already. I sent this to you last week, and the name of the file is ARMA-Alcoa. This name, ARMA-Alcoa here. See my mouse? Okay, so this is the data. If you take a look to the data, guys, let's do a view, a very simple graph, linear graph. What do you think about this, the stationarity of this series? Is it stationary or non-stationary?
Non-stationary.
Definitely. You know, the easy way of seeing if it's stationary or not, guys, just take a couple of intervals. So imagine let's do 100 observations in the first part. And let's do 100 observations between 2,000 and 200 and 2,500. Just compute the mean. The mean in the first part is going to be around 10. Do you agree, more or less? And the mean in the second part is going to be around 30. So remember, stationarity, what requires is that the moments of the distribution, just taken in the same intervals, are exactly the same. If you just violate one of them, in this case, the mean, then everything is wrong. So this means basically, guys, that this is not a stationary series. Okay, now, if you take a look to the, if you go view, correlogram, okay, levels, that's okay. Take a look to what happens. This is exactly what I was telling to you guys, remember? My partial correlation has this one here. It looks like an R1, correct?
Yes.
But what is the coefficient of the R1? The psi? The psi is going to be 1. What is the meaning of 1, guys? Remember, if there is a shock, it moves and it never returns. It's never mean reverting. You see that? So it moves up and then it stays there. There is another shock up, moves up and never returns. Remember, the stationarity condition simply means that if you have a shock, you move up, and then suddenly, eventually, you go back to the mean. Got it? And an explosive process is that you move out and then you start moving out infinitely. Okay, so obviously this is not, there is a test that we're going to learn later, guys, but you just seeing this one here, you can say, oh, come on, this is not a stationary series. Good. So how do we do it? How do we start in finance? How do we make the series stationary? Just take the log difference or the returns. Okay, so what I've done here is I've took the d log. That is an approximation of returns. Correct. Now let's take a look to the graph. You see? Now, if you take the mean, for example, in the first part, in the first 100, and you take the mean in the next 100 between 2,000 to 2,500, the mean is going to be very close to 0. Do you agree? However, guys, weakly stationarity also implies not only that the mean is equal, but also that the variance is constant. Agree with me? Now, if you see that the first 100 observations, the variance is going to be, you know, kind of, let's say like that. I cannot measure that like that. If you see that, let's assume before you see that there is a jump in volatility before the 2000 observation, the observation 2000, you see that? That one, the volatility is going to be much larger. So the second condition is not being satisfied in the stationarity process. And that's what we're going to be dealing later. So that's the Garch-type models. The Garch-type models are going to help us model better this type of behaviors. But in general, we assume that returns are stationary, so we can continue working with ARMA models. Okay, ARMA Garch models are always with stationary data. Please remember that. Okay, okay, I have my data. Now what I need to do technically, guys, is how do I select my model? And what you do, guys, is basically you do a grid. Okay, and let me show you normally what you do. Now what is interesting is that e-views presents the results very quickly and almost immediately. But what you normally do is the following. As soon as we need to select models, so you say, you know what, let's start my R component here, my MA component here. So I start with 0, 1, 2, 3, 4, 5, for example. And here I have 0, 1, 2, 3, 4, 5. Got it? And then what you start to do is, okay, I start working with the ARMA-1, for example, and I will annotate here the Kaique and the Kaique information criteria and the Bayesian information criteria. I will do only 2, just to show you how the dynamic works. And you're gonna see how easy this works. Okay, so let's do this together. If you want to run an ARMA-1, guys, this is the way you do it. You go, sorry, let me move here. You go quick, let me delete this one here. You go again, quick, estimate the equation, and then you write here the equation, right, as usual. So if you do that, the equation is going to be this one here. So I have my returns of Alcoa, my constant, this is my R1, and this is my MA1. So what model do I have here? ARMA-1. Agree with me? Make sense? Okay, so if you run this model, what we are interested here is that you just copy these values here. The Kaique is this number, minus 4.778228, and the Schwartz criterion is minus 4.771884. You normally use all the decimals, guys, okay? You don't round them, you use all the numbers here. Now, let's do the following. So let's do an ARMA-1, If we do an ARMA-1, guys, the model is simply returns, constant, AR1, MA1, MA2. Got it? You understand how to fill the model, how to create ARMA models? Okay, so you run the model, and what is interesting here is, again, simply these numbers. So at this point, you don't care about the coefficient estimates, you care about the information criteria. Got it? So now, and then of course, what you start doing is you start filling this table here. Got it? And then at the end of the day, you're going to have a bunch of numbers here, and what you do is you select the minimum. Okay. Now, in general, not normally, but in general, the Kaique and the Bayesian information criteria, or the Schwartz, give you the same result. Okay. Not always is the case. If you don't have this case in which you know what the Bayesian tells you something and Kaique tells you the same stuff, normally what you do is you go to the forecasting, and then you decide based on the forecasting. Okay. I will not fill the table here. What I will do is I will show you simply the ABUs and what you do. So in this case, what we need to do simply, guys, is to compare which one, in terms of the Kaique, which one is smaller? Model ARMA-1 or model ARMA-1.
ARMA-1 is smaller by a very small amount.
Yes, but you know, that's the interesting stuff here. It doesn't matter. Just it's smaller. Got it? So, and that's why the one that you select. Now, if you have this model here, it's very close to a model, for example, a 5-5. Okay, so the number of lags is 5 in the R, 5 in the MA. So in that case, you say, you know what? No, I prefer a parsimony model, so I select the smallest one. Got it? But when you have competing models like this, that is a 1-1 or 1-2, yeah, they are kind of indifferent. So you prefer to select the one that has the smallest information criteria. Now, what you can see here, guys, is the other thing. Which one is small in terms of the Schwartz? The 1-1, correct? So you have a discrepancy here. So what you normally do is you do 2 forecasts. You use this model here first, and you use this model here first. And then what you try to do is you try to see which one forecasts better. Got it? Make sense? So we have done step number 0, that is stationarity. Step number 2, we have selected, I say, you know what? Okay, let's select ARMA-1 as our best model. So I have selected my best model. Once I have selected my best model, I get rid of this one here. And then I simply run, and now I will pay attention to the coefficients. Now I see, you know what? I see the coefficients here. They are significant, except the constant. Don't get afraid about the R-square, guys. It's extremely small. You agree? That's the issue with time series models. You know, forecasting the conditional mean of returns is almost impossible. Got it? So that's why we need to improve the model. And that's what we are going to be doing during these classes. Okay. So this means basically, guys, that the volatility, the variance, the variability of the lag of Alcoa explains almost nothing of the variance of Alcoa, of the returns of Alcoa. Right? And this is normal. So you cannot forecast returns. Otherwise, you should have been. Otherwise, everyone should be extremely rich here. Okay? But the idea is that we're going to start improving the models with the next classes. Okay. So now what we do is, okay, so let's first of all, I need to be sure that I've done a correct. Oh, no, I don't want to forecast. I want to be sure that I have my residuals here, are the residuals of this model. So what I will do now is I will test. Got it? I will test if indeed my residuals are white noise process. Got it? So what I do for that, I need to generate a new series, remember, and I will call just R, okay, equals receipt. So I just need to simply, all the values of receipts are going to be deposited in R. So you just click here. So these are my residuals. We can take a look to the residuals, just graph them. So these are my residuals. Now, if I want to take a look, if we have an R1 process, sorry, an stationary process. So basically what I can take a look is to this one here. You see, apparently, yeah, the model is doing a good job. So we don't have this kind of weird behavior with a unit root test. Everything looks very small. So I can argue, yeah, you know what, my ARMA model, yeah, is capturing decently well. It's capturing decently well my results. Remember, the null hypothesis is there is no autocorrelation of order 1, no order autocorrelation of order 2, etc. This is my null hypothesis here. This is my Lumbox. So, and 97, this is my p-value. So this p-value is larger than 0.05. So you do not fail to reject the null hypothesis. So basically, we don't have autocorrelation of order 1, 2, 3, 4, 5, etc. Got it? Make sense? Questions, guys? Okay, so we have done the 0.3, I think. And now let's go into the forecast. How do we do forecast here? In a very simple way. You just click forecast. And this name here, guys, is going to be the one that that is going to create, the EBIOS is going to create a new variable with F mean forecast. You can change the name as you want. And let's forecast, guys, for example, 2780, for example. Let's forecast it's 31 observations. Now, you have two types of forecasts. You have the dynamic forecast and you have the static forecast. Let me explain that in a minute. So what we are going to be doing, guys, okay, if we have a time series, okay, I have 2,811 observations. What I will do is I will use only 2,779 observations. So, and from here up to here, what I will do is I will use the data to compute my parameters. So I will compute, sorry, this is phi 1, I think it's theta 1, theta 2, right? Because it is an ARMA 1, 2. Okay? So we'll compute all my parameters. So these are estimated parameters up to here. Now, from here, if I want to do a forecast, guys, we have two types of forecast. One, the dynamic, okay? So what is the dynamic, guys? I only use these coefficients here, and then I forecast from here to the future in a single run. Okay, so dynamic uses the parameter estimates up to 2779, and then simply estimates or forecast all the values up to the future. And the static model, okay, the static model does something different. So the static model, first of all, computes forecast 1 day ahead. Please, if you pay me attention, forecast 1 day ahead, uses all the data, including this day, to compute the new parameters. After that, computes the new day ahead. Once it has forecasted the new day ahead, it computes, uses the data to compute again, to recompute again all the parameters, and then computes 1 day ahead and 1 day ahead, etc. This is the static model. Do you understand? So the dynamic uses only the parameters that have been estimated before the period you want to forecast, and that's it in a single run. And the static, no, the static is moving one, okay, forecast, include this data, compute again everything, compute a new parameter, one more, compute the forecast, include the data, run again, compute the coefficients, etc. Okay, so this is the static. Make sense? Okay, so if we see this,
Professor,
yeah,
Professor, question.
no, could you
Oh.
go over that just a little bit more? It didn't
yeah. So
quite sense.
imagine in the dynamic, okay? In the dynamic, you want to forecast from here to here. In both models, you want to forecast from 2780 to 2811. Got it? And then you know this is your training set. So you use the data in the first period up to here, and then you compute the parameters. Make sense? Now, in order to forecast, you use these parameters in order to, and then you start computing forecast for day 1, day 2, day 3, day 4, day 5, day whatever, day 31. In a single run, you simply run the forecast using these coefficients here. Make sense? Guys, the dynamic is clear?
Yes.
Yes. Okay, now let's go to the static. Perhaps in the static, what I will do is I will draw something more down. So in the static, it's like that. I have my coefficients, you know, C1, theta 1, theta 2. Then I forecast 1 day ahead. Okay, I do my forecast. I do Y2780. So I forecast this one here. And in order to forecast my Y2781, what I need to do is I include the data. I include the data up to here. So what I'm doing is I'm basically changing my training period. So my training period now is going to be including 1 more day. And then I compute again the parameters. Okay, we'll do this with 2 hats. And you see, so what I've done is I've included 1 day of information. I've recomputed my model, and then I have another parameters. Well, hopefully they should be very close to each other, right? And then once I have these parameters, then okay, then I do my forecast for the next day. Got it? And once you have done this forecast, in order to do the forecast for Y2782, what you need to do first, you need to include this new day up to here. And then you do exactly the same process as usual. Make sense?
Yes, thank you.
Quick question. Under this concept, wouldn't the static model be far more computationally costly than the dynamic one?
Yeah, but yes, but in these models here, you know, computation is not a big issue. If you don't have big data sets, it's not a big issue. You're going to see in use, but indeed it takes more time to compute. If you have big data sets, yes, you are going to feel it. But now, guys, with the technology that we have, you don't feel it. I remember when I was doing this in the perhaps, I don't know, late 90s, you feel the computer suffering a lot. But now you don't feel it. You want to see. Okay. Okay. So let's do e-views then. Okay. So I will do my dynamic forecast. I will call this F. RAAF. I'm forecasting from 2780 to 2811. You simply click OK. I will not do that because I have this already here. And then you have this series here. So you have created your forecast. Got it? And now what you want to do, guys, is you want to simply verify, okay, how good is my forecast, at least visually. Got it? So how do you do that? What we do is we open a group. So this is my original data. I want to group this with my forecast. Right click, open as a group, and then you simply graph them. And here you're going to see that there is a problem because I'm graphing all the data. Okay, and I don't want to see all the data. I just want to see the last observations. Do you see that, guys? Guys, make sense to you? Okay, so how do we do that? If I want to change the sample, so I want to see just a specific period in time, what you do is you go sample, and then the sample that we are interested here is 2780, correct? And then you just click here. The original data is the blue, and my forecast using dynamic method is the kind of orange line. Do you see that? Of course, guys, it goes almost to 0. So it's basically taking the mean of the ups and downs. Got it? Now, if you do questions here, do you have questions? Now, if you do the other one, so let me save this one. So, so this is, yeah. So this is ARMA 1-2 dynamic forecast. Okay, so if you do the group now, this one here is the static forecast. So what I've done here is basically, what I've done here is forecast. Instead of using the static, the dynamic, I simply use the static, run the regression, and then you take, I call this one SM. Okay, you run this one here, and then this is what you get. So if you want to compare again, let's do a group of these two guys, open as a group, and then we can simply graph. And then you see, you don't see much difference in this case. This is strange. Give me 1 second, Alicia. Give me 1 second. Just to be sure, I will just call static. Yeah, you can see, guys, there is a small difference, a small point here, but it's nothing. It's nothing. Okay, and okay, guys, questions. So that's the way we do the time series. It's very simple. It's straightforward, and this methodology is going to be repeated always. Okay, so what is going to be next, and what I will please require you is I will create a couple of videos about gauge models. So next class I will have, the first 20 minutes I will ask questions, I will answer questions. I will do a new run of a model, and you ask me questions. Okay, it's going to be more interactive, and then we can go into bar models after that. Okay, guys, we are going to stop here. We stop here, and then we go for quiz number 2. Questions?
Professor, is there any way you can upload your class lectures slightly earlier than usual? Because you usually
yes, you know what? I asked for them, and they did it this Friday, right? No, I think Thursday. Yes, I asked them. Don't worry, I will ask that for they always the excuses that they have tons of people. I don't know why. Okay, guys, I will do this for you. I will try to have it for tomorrow or Friday early, so you can start reviewing and working on that. Make sense? Okay, guys, so please, the only thing that you need with you is calculators if you want. I don't think you need it, but just your pen, move your notes, close your e-views, close everything. We just need you. Okay, no notes, guys, it's independent. So let me close this one here. Okay, so let me do a new share. Okay, so we'll start in 1 minute. So I will send you, give me 1 second. I will send you the exam right now. As usual, guys, please, what you need to do is you need to use quiz2 _ username. Do you understand? So when you send me the PDF, please, one single document. Don't give me 10 documents. It's one single document, and use just the space that you have allowed. Okay, so I have sent this to you, so if you can take a look, please. You need to be, all of you need to be with a camera on, please. I need to have you camera on, so this is regulation for them. I need to see you all the time. Okay, Shui and Lou, can you please turn on your cameras?